It carries enough venom to kill 26 adults. It fits in a child's palm. And it looks exactly like a wet pebble. Hapalochlaena lanulata. The blue-ringed octopus. Body length 8 centimeters. Weight less than 30 grams. At rest, it is brown, mottled, unremarkable. The same color as the gravel and shell fragments it settles against in shallow tide pools along the Australian coast. That is the problem. People pick it up, not out of recklessness, out of genuine curiosity, because nothing about this animal announces itself at rest. A child reaches into a rock pool. The octopus sits still. It does not flee. It does not bite immediately. It simply waits, small and calm, in a cupped hand. The rings only appear when the animal is agitated. 60 iridescent blue circles, blazing to life across the mantle in a fraction of a second. Electric, unmistakable. But by the time those rings ignite, the animal is already stressed. The window between this looks harmless and this has already bitten you can be seconds. And the bite itself leaves almost nothing. A small prick. Sometimes nothing at all. Williamson and colleagues documented this in 1996. The octopus does not inject venom in the conventional sense, but allows the venom to flow from the salivary glands into the wound. No fang, no visible puncture. The beak, smaller than a fingernail, does the work quietly. The first confirmed human fatality was September 18, 1967, James Ward, Stokes Bay, South Australia. He was a young man. He picked one up. He was dead within hours. Here is what makes this creature unlike almost anything else documented in coastal waters. There is no antivenom, not a limited supply, not an experimental one, none, anywhere on Earth. By the end of this video, you will understand exactly what happens inside a human body after that bite. The specific biological mechanism, the specific reason no antivenom can exist, and the account of one victim who survived and described the experience from inside the paralysis. Here is the assumption that gets people killed. The blue rings are a warning. Everyone knows this. Bright, unmistakable. The animal is telling you to let go. So the logic follows: if you see the rings, you drop it. Simple. Safe. Case closed. Except the rings appear after the bite. Roy Caldwell at the University of California, Berkeley documented this in 1982. The chromatophore organs that produce the display activate when the animal is agitated. But agitation and biting are not sequential. They are simultaneous. By the time the rings blaze, the venom is already moving. The bite itself tells you nothing. Sutherland and Lane, writing in the Medical Journal of Australia in 1969, described what follows. The victim may feel numbness of the lips and tongue, followed by difficulty breathing, and then paralysis and respiratory failure. That progression sounds dramatic, but it is not fast. And it does not start on the beach. James Ward was 18 years old. September 18, 1967. Stokes Bay, South Australia. He picked up a small octopus. He felt almost nothing. He walked back up the beach. He was dead within 2 hours. The Australian Medical Journal published the full case report in March 1968. Ward showed no immediate distress, no visible wound, no reason to stop moving. That is the mechanism that makes this animal genuinely dangerous. Not aggression, not size. The bite is painless, the mark nearly invisible, and the venom does not announce itself. Victims walk away, feeling fine, sometimes for an hour, sometimes longer. A teenager leaves the waterline, hand in pocket. Nothing in their posture suggests anything is wrong. The warning system works. The rings are real. The danger is visible, but only to someone who is already too late. Which raises the question the Ward case never fully answered. Once the venom is moving, what exactly is it doing? Here is what tetrodotoxin actually does. It does not stop the heart. It does not attack the brain. It finds the motor neurons, the electrical wires running from your spine to your muscles, and it blocks them. Specifically, it plugs the sodium channels those neurons need to fire. No signal gets through. The diaphragm stops. That is the muscle beneath your lungs. The one you have been using, without thinking, every 3 to 4 seconds since the moment you were born. When tetrodotoxin reaches it, the muscle simply ceases. The lungs do not inflate. The body begins to suffocate. Here is what makes this different from any other venom on Earth. Your mind stays completely intact. No sedation. No loss of consciousness. A 1989 case report published in Clinical Toxicology, Volume 27, documented a survivor who described the experience from inside the paralysis. The words recorded in that report: "I could hear everything, aware, immobile, unable to breathe, wailing." The reason no antivenom exists is not a funding problem. It is a structural one. Tetrodotoxin is a small molecule. Antibodies, the mechanism behind every antivenom ever developed, require a large protein target to bind to. A research team at the University of Queensland confirmed in 2009 that tetrodotoxin's molecular architecture makes antibody development functionally impossible with current science. The whiteboard answer in laboratories working on this problem is blunt: no antibody target. The only treatment is a human being. A bag valve mask. 2 hands compressing rubber in a steady rhythm, forcing air into the victim's lungs manually for 4 to 6 hours until the toxin clears the system on its own. 4 to 6 hours by hand, without stopping. In April 2006, a young boy in Victoria, Australia, survived a bite after receiving mechanical ventilation for 10 hours. The machine did not save him. The decision to keep going saved him. Remember the child's palm from the beginning of this video. That wet pebble shape, the size of a large grape. This is what it carries inside. Not aggression, not malice, just chemistry so precise it can unmake a human nervous system without touching a single thought. The evolutionary question has no clean answer. Why did lethality at this scale develop in an animal this small? Brian Fry's 2009 analysis confirmed the toxin is not even the octopus's own. Bacteria in its salivary glands synthesize it. The animal inherited a biological weapon it did not build, deployed through a bite that leaves almost no mark, in a body that fits in a coat pocket. Science has logged the mechanism. Science has not explained the proportion. The Deep Index files this one under the category it has earned. A creature whose danger is invisible, whose venom has no counter, and whose only known treatment is another person choosing not to stop.